Hello everyone. I'm going to go over the Exam 2 review. It's going to be, of course, an e-learning online exam, and it will use the same HonorLock settings as the last exam. There are about 40 questions worth 2 to 4 points each. You should not use any external notes or resources except for this one resource right here. All right, in Piazza on the resources page, we have the reference sheet right here. This URL will be whitelisted during the exam, so you could open this up before the exam and it should be no problem for you using this during the exam. There are a few short answer coding questions. Most of the questions are true, false, or multiple choice. It's an hour 15 minutes. One attempt. Questions are randomly drawn from pools of questions presented one at a time without backtracking. These are the sections of the book that are covered on the exam, and these correspond to the assigned videos since the last exam. All right, let's get into the problems. You could have a couple of problems, one where we convert some smallish floating point number to the IEEE format, and another where you go the opposite way. You're given the hex representation and you have to figure out what number it is. The problems will only involve the single precision format, which has 1 bit for the sign bit, 8 bits for the biased exponent, and the rest of it for the mantissa. So the first thing to do is to convert the whole number part to binary, which I've done here. So the question is, how might you do this without scratch paper? One way you might do it is just to write for yourself the place values. So for example, I'm not going to start with 32 because this number is less than 32. I'll start with 16, 8, 4, 2, 1. And then I'll ask myself, can I subtract 16 from 21? Yes, so I'll put a 1 there. And 21 minus 16, I'm just kind of typing my scratch paper. That is 5. Can I subtract 8? No. Put a 0 there. Can I subtract 4? Yes. That leaves me with 1. Okay, so that made it easy. Here's my 1 here, and I put a 0 there. So you may be able to do this more in your head, but I'm just kind of showing you an alternate way if you're more of a visual person and like to visualize that. So this is the whole number part, 10101. And then the fractional part for 0.25 is 0.01. On the test, you'll either have 0.25, which is 0.01, or you'll have 0.5, which is 0.1, or you'll have 0.75, which is 0.11. These are the only 3 fractions you'll have. So how does this work? I go over this in the original video, but let's just talk about it for a minute. Just like we have a place value for each binary digit to the left of the point, we have a place value going to the right. So this first place value is really 1 over 2. That's 1/2, which is 0.5. This place value is 1 over 2 to the 2 power, 1 over 4, 1/4, which is 0.25. And then 0.75 would just be adding these together. So those are the only 3 fractional parts you will encounter on this test. Once we put together the whole number part and the fractional part, 21.25 is this number in binary. That's not normalized. We have to normalize it before it can be stored in the IEEE single precision format. So that means we need to move this point 1, 2, 3, 4 places. So that gives us 1.010101 times 2 to the 4. All right, so once we do this work and get the number normalized, we're ready to put it into the format. This is a positive number. That means the sign bit is going to be 0. Our real exponent is 4, We add the bias of 127, it's always 127, and we get 131. And now we have to represent this 131 in 8 bits of binary. Again, you can use place value. This first bit here is 128. So if I subtract 128 from 131, I need to come up with 3 more bits here. And this is 3 right here, 2 plus 1. So you can use place value here as well. And then the fractional part is everything left over. 0, 1, 0, 1, 0, 1. Keep in mind that we don't store this 1 before the point. We don't store that anywhere. So putting that all together, we have our sign bit, we have our 8 bits that are our biased exponent, and then we have the rest with trailing zeros for the fractional part. If I retype this here, I can put that in groups of 4 bits. After I type it, I can scooch it into 4-bit groups. And then I can easily convert that. This is 4, 1, A, and the rest are going to be zeros. So you'll need to put your answer in binary form in order to figure out what it is, but your final answer is going to be this hex right here. And you'll need to show your work at least at this level. You don't have to type out sign equals, biased equals, and all that. You would at least need to show how you got to this answer. All right, now let's go the other way. Let's say you're given this hex. We want to know what decimal number that is. First thing to do is expand the hex into binary. Okay, so this is C15, C, and then all zeros. Now I'm going to regroup to make it easier for me to read this. So this is just retyping it, but putting it in the correct groups. So the first bit is the sign bit, the next 8 bits are the biased exponent, the rest is the fractional part. The sign bit's 1, so I know it's a negative number. The biased exponent here, again, this first digit is 128 plus 2 is 130. And then 130 minus my bias is 3, so my real exponent is 3. I type the 1 dot, again that's not stored anywhere in there, that's assumed. And then I type the fractional part, which I got from here, times 2 to the 3. All right, this is the normalized number. That's really impossible for me to look at that and say what number that is in decimal. So first I need to unnormalize it by moving that point 3 times to the right, and then I get 1101.11. Now this is a number I can understand. 1101 I can figure out by even counting that that's 13. And we've already talked about 0.11 is 0.75. If you want more practice, you can always use that site we talked about before to come up with some numbers and then see if you can manually get through the process to either go either way, from the number to the hex or from the hex back to the number. And the numbers on the exam will be fairly simple like this. All right, let's talk about the computer performance. Let's look at the review real quick. Notice I've got Amdahl's law here and CPU time formula here, 2 different versions of it. So suppose you have a machine which executes a program. You've got 50% multiply, 20% divide instructions, and the remaining instructions are other. So that's our baseline. 50 plus 30 plus 20 is 100%. Can we beat that baseline? Well, we could make the divide 3 times faster. We could make the multiply 8 times faster. If you could make only one improvement, which one would you do? Well, let's say we want to make the divide 3 times faster. All we do is take that 20 and divide it by 3 and leave the others alone, and we get about 87. Now on the test, I'm not going to ask you anything like 20 divided by 3. It'd be more likely to be 20 divided by 4, 20 divided by 5. I find that students can do those in their head. That's not really hard. I think everyone knows that basic multiplication table facts is basically what that is. So you won't have anything odd like this. Same for this. Now let's find the multiply. 50 divided by 8, again, you're not going to have any weird number like that. It'd be more likely to be 50 divided by 5 or 50 divided by 10, for example. And leave the other two alone, and we get 56.25. This is a lower number than here, so if we could only choose one, we'd choose the multiply. If you made both, well, I just put both of those in the calculation here. And I'm asking this on the review, what's the speed relative to the original machine? I won't be asking that on the exam because you don't have a calculator. But I just included it on the review so you'd get a notion, a little more familiarity with the idea of relative performance. So the original performance, we're calling it 100. Divide it by the other time here, and we see that it's 2.3 times faster. Again, I won't be asking you to do this kind of calculation on the test. Question 2 here on the review is we're comparing two computers A and B that have different clock rates, different CPIs, cycles per instruction, and when compiled, the same program compiled from computer A has 100,000 instructions. For computer B, it has 60,000 instructions. So if you put all those in the formula, which again is listed over here, and multiplied it out, you get these answers here. Now, on the test, I won't be able to ask you this type of question because, again, I don't want to use calculator questions on the exam. I'm really more interested in, do you understand the concepts? Do you understand the concept of this formula and the role that each of these three parts plays? So there's three parts to calculating CPU time. It's how many instructions are there, and what is your average cycles per instruction, and either your clock cycle time or the clock rate. These are the same things. One's just inverse of each other. So I'm not going to actually ask you questions like this on the exam to calculate them. I just put these on the review to get you thinking about more conceptually what's the role of each of these components. So this question number 3 here is basically just an algebra question. You have a missing value, you solve for the missing value, and calculate the CPI. So again, that won't be on the test, but hopefully it gets you thinking about the importance of different components. Same for this part here. The spec ratio table for a given program, it shows their instruction counts, CPI, clock cycle time. So this is really our formula we just looked at. This is our instructions times CPI times clock cycle time. We get our execution time. So here I have you go through for two of these programs calculating, just so that will reinforce the idea of that formula again. And you get slightly different numbers because they rounded. For example, you know that the instruction count is not really 2118 and then a bunch of zeros, right? So they rounded here, and that's why we get slightly different numbers, but not enough to make a significant difference. The important part of the spec table is that we have all of these execution times for all of these different programs for a given computer, and we want to compare that to some baseline, some reference computer, which is going to be an older CPU. And the way we do that is we take the reference time and divide it by the execution time to get this spec ratio. So this spec ratio is saying that the new computer runs this particular program 15 times faster, this one 11 times faster. All right, that's it for performance. All right, here we have our non-pipelined implementation. And what I'm asking you here is to convert this AND into the binary, into the machine code. So again, I can look at the review sheet and see that AND has an opcode of 0 and a function code of 24 hex, and of course it's an R type. So I can start converting that to binary. I need 6 zeros for the opcode. The format, which is on the sheet, tells me that it's going to be RS, RT, and then RD. And then shift amount is going to be 5 zeros. And then I'm going to have 6 bits for the function code, which was 2, 4. And so here's the 2, and then here's the 4. All right, so let me figure out the rest of these. S1, that's my RD. S1, if I look on the reference sheet, let me go ahead and do that. Here's my R format. S0 is 16, so S1 must be 17. So S1 is 17, and if I want to express that in 5 bits, that's going to be 1, 0, 0, 0, 1. Now I have T3. The same reference sheet tells me that T0 is 8. So if I really want, I can count up on my fingers, or if I don't want to count up on my fingers, I can just type myself a little helper right here. And T3 is 11, which in binary will be 0, 1, 0, 1, 1. So if T3 is 11, then T4 must be 12, and that's going to be 0, 1, 1, 0, 0. All right, now I just need to put these in here. So I can replace my RS with this value here. RS is T3, which is 0, 1, 0, 1, 1. RT is T4, which is 0, 1, 1, 0, 0. And RD is 17, which is 1, 0, 0, 0, 1. All right, so I did the binary part. Now I need to regroup these into 4 bits. 4 zeros. All right, so that is hex 0, 1, 6, C, 8, 8, 2, 4. That is my final answer. Not sure why I put spaces there. That's my final answer, and here I'm showing how I worked it out. I say trace the path of the instruction here. Well, I can't actually have you do that on an online exam, so I'll ask you more questions like what goes on here and where each of these bits go, and I'll ask you multiple choice questions about this. So where does the opcode go? The opcode goes up here to this main control unit. And then for an R-type instruction, we have RS and RT come in right here. This is RS, this is RT. Our RD register for an R-type instruction is going to go in here. And what happens, of course, is that those two RS and RT registers are read. They are ANDed together. The output comes here, bypasses data memory, goes through that multiplexer, and is written back to the destination register S1. So you need to understand that because I'll ask you questions about it, but you won't actually be tracing. Tracing is just something to do on the review so it helps you understand what's going on. And so I'm going to ask about the multiplexers and the control signal settings. So we have 4 multiplexers on this diagram. Let's talk about what they do. This multiplexer right here, just to the left of the register file, determines which bits are picked off for the destination register. So for an R-type instruction, the destination register is in the RD position. So these bits will be picked off. And notice that they're pointing right at the 1. So that indicates that that control signal, which is register dest, that needs to be a 1 for an R-type instruction. All right, this multiplexer is controlling what is the second argument. So just to the left of the ALU, we have this multiplexer, which determines where this second argument comes from into the ALU. The first operand is always RS for any type of instruction. You can see that in the diagram here. For an R-type instruction, which we're talking about now, the second operand comes from the register file. So notice that's pointing at 0. All right, so that tells us that ALU source needs to be 0 for an R-type instruction. This multiplexer controls what's being written back to the register file. So in the case of this AND instruction, we bypass data memory. Notice that points at the 0. And so that tells us that mem to reg needs to be a 0 for an R-type instruction. So it will pick up this signal to write back. The other control signals are basically, think of them as true, false. Is it a branch? No, so that's 0. Are we reading from memory? No, that's a 0. I'm not going to ask you about AL op. Are we writing to memory over here? Nope, that's a 0. Are we writing to the register file? Yes, we're writing back to the register file, so reg write would need to be a 1 for an R-type instruction. These are the kind of questions conceptually I will ask about for the role of the multiplexers. I just described that. I'll ask you conceptual questions about that. And then you can, again, you don't need to memorize any of these control signals because I've just shown you how you can read them from the diagrams. And you can also just kind of ask yourself the true-false questions that we just went through. All right, let's look at a load word and see how that works. Let's look for load word is right here. It's an I-type instruction and its opcode is 23 hex. And here's a reference for the I format if you need it. So my opcode comes first. That is 23. So there's my 2. And this has to be in 6 bits. There's my 3. That's my opcode. And then the format says that we have our source register, RS, which is going to be the T0, and then we have RT, and then, which is our destination register, and then the rest of the 16 bits here is going to be filled up with this 8. So again, we have the same destination register here, RT, that's still 17, 1, 0, 0, 0, 1. We have T0, which is 8, that's our source register. 8 is 0, 1, 0, 0, 0. And then the rest of this is going to be filled up 16 bits here with just this number right here, 8. So let me rearrange that a little bit to get it more hex friendly. 1101, 0001, 0001, a bunch of zeros, and then finally 8. So if I want to put that in hex, that is 8D, 1, 1, a bunch of zeros, and then 8. So how many zeros? There need to be 4 hex digits, so that's 0008. All right, again, you could practice this by typing in the instructions in Mars, hitting a symbol, seeing what you get for the hex, and then working forward towards that. Or going the other way. Look at the hex and go back to the instruction. Let's talk about the control signals and how the multiplexers and how all that works, how the data path works for a load word. Again, opcode for 6 bits, the 23 comes up here. In this case, our read register is RS. That goes straight through to the ALU. Our destination is now RT, which is in this position. So that tells you that this multiplexer control signal needs to be a 0. And backtracking, we see that register destination needs to be a 0 for a load word. For the second operand, for a load word, remember what the ALU is required to do here is to add the contents of T0, which is going to be right here, the first operand, to 8. So this needs to be an 8. That needs to come from the lower 16 bits of the instruction. It gets sign extended, and then it goes through this multiplexer. And notice it's pointing to 1. So that tells us that ALU source needs to be a 1 for either a load word or a store word. So remember that load word and store word, you're doing the same calculation of an address. All right, so that address comes into data memory. The contents of that location are read, and notice that points right to the 1. That tells us that mem2reg for a load word is going to be a 1, and that gets written back to RT. If this had been a store word instead of a load word, the address calculation is identical. The only difference is this value has to be read as well. We can kind of see that it's read here and it goes through this separate path here so that we know what to write to memory. And of course we're not writing back, if it had been a store word, we're not writing back to the register file. And then we can just ask ourselves the true false based on whether are we writing to memory, are we reading to memory. It's basically 1 or 0. Let's look at the branch equal. We can see that that also uses instruction format I, and its opcode is 4. So let's think about that. Opcode is 4. Let's put that in 6 bits. There's my opcode. That of course is going to go here. And then we're going to have RS, RT, and then whatever offset exit will be. And if you don't see the whole program, you won't know. So obviously I can't ask you about the offset. RS and RT are T1 and T2. T1 is 9. T2 is 10. All right, for a branch instruction, we don't have a write register. So this multiplexer register dest is a don't care. Same for store word. Whenever something's not relevant, it's a don't care. We read the contents of RS and RT straight into the ALU. So since we're reading RT here, that means that ALU source is going to be 0 again for a branch instruction. We read the two values. This is a branch equal, so the way that it compares if they're equal, it subtracts them. And if the result of that subtraction is 0, this 0 flag will be true. We'll have a 1 here into this AND gate. It is a branch instruction, so this will be 1. And again, all of these signals right here are determined solely from the circuitry here. The only input is the opcode. So all of these are deterministic based on the opcode. So if it really is a branch, and we really are going to branch, T1 and T2 are equal, then this AND gate will result in a 1 to this multiplexer right here, which will mean that instead of just updating the PC by 4 as normal, we're going to update it by whatever comes out of this little adder up here. So what does come out of that adder? What we do is take that offset, which in this case we don't know exactly what it is, but we know that it's 16 bits. It's going to get sign extended, go way up here, get shifted left 2. The reason it gets shifted left 2 is we want it on a word boundary. Basically, the offset is in words, and we want it actual addresses. And that gets added to the current value of the PC, which has already been updated by 4. So the purpose of this multiplexer up here is to determine how the PC is updated. Is the PC updated by 4, like in a normal, instruction one after the other? Or is the PC going to be updated to some new target address? That's the purpose of this multiplexer. So that is a review of the review. We've talked about how to convert numbers in floating point. If you understand how to read the basic floating point instructions, you should be fine. Translating and starting a program, that refers to what is the compiler, assembler, linker, loader, what's the role of all that, as well as static versus dynamic linking. In terms of comparing and contrasting these different architectures, I'm not going to get into the weeds on these differences. The questions will involve very basic high-level differences between these architectures. We went over in detail the computer performance questions. I'm pointing you to a specific location in the book. Here's what I'm talking about. On the left, they show basically an array indexing approach to a loop that clears an array. On the right, they show the pointer version. And we talked about this in the video as well. So if you're given this code, you need to be able to rewrite it like this or vice versa. The first part of Chapter 4 is this non-pipelined implementation and the control signals that we've been talking about, and then some general MIPS coding questions. These will be similar to the first exam, small coding snippets or questions where you're given some code and asked questions to make sure you can read code and understand it. I believe I have answered most of the questions that I've seen out there on Piazza. I'll be keeping my eyes open for new questions between now and the morning when the exam opens, and after that I really can't answer any questions about it.